Today we're going to end up at the idea of Kepler's laws of motion, but I want to do a little bit of a sort of a talk about how we get there rather than just sort of dump them on you. So a little bit of a sort of a history lesson. For those of you who are trying to scribble notes or everything, I'll tell you when it is you actually need to have something down. So if we go back to the ancient Greeks, whose ideas would dominate our understanding of the Earth and the solar system and the universe, therefore, they had a view, firstly, that the Earth was definitely round. Okay, they didn't think the Earth was flat. They thought the Earth was definitely round. They even knew about how round it was. They knew it was about 40,000 kilometres over and around the circumference. And at this point, even this early on, what I want you to do is to just pause this video and switch to the one on a person called Eratosthenes by Carl Sagan, where you'll get to enjoy his phenomenal turtleneck sweater. Excellent. So having done that, you know that they know the Earth is round. That's an idea that doesn't disappear. The idea that everyone thought the Earth was flat until Columbus was kind of invented in a biography of his in about the 1800s. So they know the Earth is round, and so they are standing on the Earth, and so they're looking out into the night sky, and they can see the distant stars, which appear to be in a circle. And then you've got the other things. You've got the sun, and you've got the moon, and you've got the planets, say, like Mars. And as far as they were concerned, they figured that everything was moving around us. So the reason that you get day and night circles is because not because the Earth is rotating, but because the sun is going around the Earth once a day, which is, would mean it was moving quite fast. And Mars is also going around the Earth, but at a slightly different pace. And even the background stars, which are harder to rotate around, even the background stars are all going in this sort of like this direction. And they're all travelling at different speeds, but essentially you have the sun, the moon, the planets, which is a word that means wanderer, and the fixed background stars. That is the universe as far as the ancient Greeks are concerned. And that idea is written up, it comes around from about 500 BC from people like Archimedes and Aristotle and so on. But it becomes really popular because of a fellow called Ptolemy, who lived in around about 150 AD in the eastern part of the Roman Empire. So he is someone who's very influenced by the ancient Greek classical things. He writes a book called the Almagest, and in it is essentially a repository of all classical astronomy. That is the names of the constellations, data, tables, information of how things work, but also this idea of how the universe is, with the Earth at the centre. And this leads to a rise in something which we call the geocentric model, Earth at the centre. And this was exceptionally popular for both reasons of philosophy. It's lovely to think of ourselves as the centre of everything, and religion, because that's what a lot of religious sort of like ideas were, is it? We are in a special place in the universe, but also for just common sense. After all, if you wanted to go back 2,000 years and try and convince someone that in fact they were on a rock that itself was rotating every day, every 24 hours, they would call you a lunatic, because if you are going to rotate something which has a circumference of 40,000 kilometers, and you're going to do that in 24 hours, that means if you're standing on the equator, you're travelling at around about 1,700 kilometres per hour, or 450 metres per second, faster than the speed of sound. Nobody is going to believe you because they would argue that they would feel it. Now, so what happened is that people said, yes, we have a lovely model, it makes sense, it makes us feel good, but the thing about scientific models is that if they do not have, if they are a model, they should be making predictions. And if things occur that disagree with your predictions, then you have to have a reason for that, and you have to solve it. And one of the biggest problems that occurred was something called retrograde motion. Now, every 2 years or so, what you will find is if you look at the background stars, so so we've got a fixed pattern of the background. I should really be drawing an actual constellation, but I can't be bothered. The background stars are fixed. They move as a group slowly over the course of each sort of day, which is fine because every day you go out, they're sort of, if you go out at the same time the next day, they're in a slightly different position, but that's obviously explained because they're rotating around us. But the planets were wanderers, and the reason they were called the planets is if you go out on a different day, then what happens every day you go out, they will be in a different position. And all the planets would do this at different sort of times, at different rates. So we have this weird phenomenon of the planets. That's where the word planet comes from. It means wanderer. So you go out, and that's why they would appear in different constellations. So when people would talk about Mars in the constellation of Virgo, that's because it literally, if you go out and look at the constellation Virgo, you'll also find at that point the constellation Mars. But a few weeks later, it'll be in the next one, and so on, which will be Libra, and so on and so forth. Now, that's all fine because, again, it's explained by this system. If they're all travelling around you at different speeds, then of course, they will be in different points at various different times. And the planets, that's absolutely fine. The problem occurred with retrograde motion. The normal motion of planets and the moon and all this kind of stuff is to move on successive days in sort of this direction, which is called prograde. Now, prograde motion that's normal, that's fine, that's explicable. But every now and again, what would happen, you'd go out and you'd see on successive days, and let's say we're imagining we're looking at Mars, and we'd see this thing, and against the background stars, suddenly what Mars would do is something that looks like this. It would do a loop-the-loop. So Mars's route through the sort of background stars would basically be this. It would be doing prograde motion. Suddenly it would go back on itself, which would be called retrograde motion. And then it would loop back on itself. And this would take place for Mars. It lasts for, a couple of months or so. So for a couple of months, Mars has gone back on itself. The next time it will happen will be in October 2022. Mars will suddenly seem to go backwards in the night sky. And that doesn't make sense. You cannot explain on a model that looks like this sudden idea that Mars is going to be trundling along happily in one direction, then suddenly decide to say, nope, I'm going to go that way, and then go along again. None of that makes sense. Now the sun doesn't exhibit this, but all the planets do at various points and times. It's hard to see that for Mercury and Venus, but it does happen. But it does happen to all of them. Now, they knew about this. Ptolemy knew about this, and they said, "Aha!" Well, they created a view of the solar system that looked even more bizarre. And at this point, I can only really start drawing one of them. So there's the Earth, and there's our planet. And our planet is on an orbit that's going in a circle. But in order to get around this, they said whilst it's going around the Earth in a circle, it's also doing a little circle on top of the circle. So it's on a secondary orbit, which is called an epicycle. And what can happen is sometimes when the planet is moving that way, but on the epicycle it's moving in the opposite direction, that is what can lead to it appearing to move backwards in the sky. So they built circles on top of their circles. Problem solved. Not quite. Because it turns out that this kind of fudge factor, every different planet needed its own kind of epicycle. And then because of orbital mechanics having, not being related this way, it didn't quite work perfectly. So what they would then have to add would be an epicycle onto the epicycle. And eventually you end up with something that's absolutely bonkers. Literally the most absolutely gobsmackingly like weird diagrams that look just like giant spirograph pieces of art in order to try and plot orbital mechanics. And they did it because eventually it would work. They would end up with exceptionally accurate predictions with this weird model of where planets would be at what point and what day of the year. Incredibly accurate, but not very helpful. And it was Johannes Kepler, it was a guy called Nikolai Copernicus in 1542, which a book got published after his death, where he realised that actually you could solve this problem with a heliocentric model. The idea that if you stuck the sun at the centre and you have the Earth going around the sun in its orbit, then Mars appearing to go backwards is actually just a sort of an optical illusion. Oops. These aren't the greatest circles I've ever drawn. Is an optical illusion that will occur when one object in motion overtakes another. And you will get a moment where it will appear that something, that Mars, compared to the background stars, which are so far away so we don't notice them shifting, the Mars will appear to suddenly be in a different position given where we're seeing it. And that action was something that suddenly started to change the world. And he released a book on the motion of heavenly bodies, I believe he called it, which said, I can solve retrograde motion if I stick the sun at the centre. Now, in order, because I'm not good at animation, there's another pause at this point to watch the next video, which is on retrograde. And it's got a nice little series of animations that show this sort of phenomena in action. All right, so you're back again. Excellent. So we've got Copernicus's model, but it doesn't quite work. So although we'd love this idea and we'd say it would be wonderful if everyone suddenly went, hurrah, we can do this use Copernicus's model and we can do that and we can solve planetary motion. The problem was that the heliocentric model, although it solved retrograde, it was worse at predicting. So if you tried to make an astronomical calendar and you used the Copernican model, you were not looking at the right patch of sky at the right time. The Aristotle model with the geocentric model was more accurate. Why? Because they'd been fudging it for 1,500, 2,000 odd years of adding these weird epicycles so they could end up, making this thing look really accurate. So what would happen is that although Copernicus's model got a bit of press, it wasn't really taken very seriously in a lot of places. It had its philosophical arguments of not putting the Earth at the centre, which caused many, many problems. So that kind of went on the back burner. It also didn't help that the person who published his book put a little foreword at the start and claimed it was in Copernicus's own writing that there was that it was just a mathematical model. It was a little idea, but it wasn't really how he thought things worked. So the next sort of like advancement doesn't really happen. This is in 1540 for another 60 odd years. And that involves, that's where Johannes Kepler is about to turn up. But slightly before him is a person called Tycho Brahe, who has a phenomenal name and also a silver nose, because he lost his in a duel. He becomes from about 1575 to about 1600, he is one of the foremost astronomers. And he is granted some land from Denmark on an island called Fen, H-V-E-N, and he builds one of the early research institutes called Uraniborg, and he basically takes observations of the night sky for over 20 years. Some of the most accurate observations. He doesn't have telescopes, but he builds sort of like observation chairs that enable him to get really accurate records of where everything is. Because he does believe there's something to Copernicus's idea, but he still wants the Earth at the centre. He's trying to build a model which kind of looks like this. Has the Earth at the centre, with then the moon going around the Earth, and all the fixed stars at the back, I'm not going to draw them all, also going around the Earth. But then what you have is the sun, which is going around the Earth, but then the planets like Mars are going around the sun. So he's trying to build this kind of, he's still obsessed with circles, still obsessed with all these weirdness, he still wants the Earth at the centre of everything, but he decides to let the planets orbit the sun and in turn therefore orbit the Earth. And that can lead to a little spirography sort of thing. In very similar way to the way the moon orbits the Earth, and yet both are orbiting the sun. So if you track sort of the Earth's motion around the sun, because of the moon, it will look a little bit it looks a bit wibbly and stuff. So Tycho Brahe is putting this all together. He eventually gets exiled from his island and goes to Prague in 1600, where he meets Johannes Kepler. And he meets Kepler, and he takes Kepler on as an assistant. Why? Because Kepler is he's becoming one of the world's foremost mathematicians. Brahe is a great person to observe and collect data, but he is struggling to put his model together. And part of that is because he's really protective of his data. He doesn't let many people see it. And he employs Kepler, and Kepler is one of the few people that Brahe allows to look at his data. But in 1601, Brahe dies suddenly. Now, he dies of I think it's a gallbladder infection of something, so he dies of an infection. There were rumours that he was poisoned by a rival, potentially even by Kepler himself, in order for Kepler to be able to get access to all the data. He was actually exhumed in 2010 to be able to test this theory, and they didn't find any trace elements of any poisons. So we feel that he just died due to bad luck. And Kepler was given the task of finishing Brahe's work, to finish this, the Brahe model. So to do this, and Kepler sets to work. He's got, by this point, probably about 30 years worth of observations, and 30 years is long enough for you to get an entire orbit of Saturn. Okay, so we are actually at a point where we've got multiple orbits for all the planets around the sun. So there's a lot of data there. That's kind of the timescale you need to be at. And he realises he can't make Brahe's thing work, but he does realise what the problem with Copernicus's model was. And so he takes control in 1601. He publishes 3 laws of planetary motion. Okay, and this is where this is where it actually turns up as being things that we need to be aware of, because this is where the A level kicks in. 3 laws of planetary motion. two of which are published in 1608 or 1609, so a mere 8 years after he takes over. One of which doesn't get published until 1620, so that is a long time, given that Brahe started his observations in 1675. This is a long project. So what does he realise? So the first law is that planets orbit in ellipses with the sun at one focus. So an ellipse is a circle is basically a very special form of ellipse. And you define an ellipse by various things. It's like almost the equivalent of almost having two centres in a weird way. So an ellipse, whereas Copernicus thought that you had a perfect circle with the sun at the centre, Copernicus realises that it's formed as called an ellipse. An ellipse will have these sort of these things called the foci. So the planet orbits the ellipse, and just at one foci is the sun. There is nothing at the other foci, nothing there. Now, a circle is just a thing where those two foci are at the same point. So it is as much in it's as much in sort of this direction. That diameter is the same as that diameter. These two things are called the two semi-major axes. The semi-major and semi-minor axes is how they defined it. It's basically an ellipse is to a circle what a rectangle is to a square. So now the reason that this hadn't been noticed before is that the sun, the orbits around the sun are very, very, very nearly circular, like almost perfectly circular. The foci is just outside the actual position of the sun itself. It's very, very close to being circular, but it's not. And that's why, over many years, there was a drift away from like Copernicus's predictions. They became wrong because they were assuming that everything was going on a circle. So that was his first realization, that the circular argument wasn't true. The second law is that planets sweep out equal areas in equal times. Now, what that means is that if you draw your elliptical orbit, it's a terrible ellipse, looks a bit like a depressed potato, and we put our sun, and we say, well, let's put our planet sort of here, and let's say that, a month later it's here. Well, that will sweep out an area from here to there, and you get this area. Now, as the planet goes around on its orbit, eventually it'll get to here, and 1 month later, let's say it's got to about here. And if we do the same thing, let's call that area B, let's call that area A. Basically, he realised that A is equal to B. Equal area, equal times, if you just had an imaginary rope and were measuring the area. Now, the actual reason for that is because planets are not travelling at a constant speed. So when you're further away, you're travelling more slowly. Anything in an elliptical orbit is following this sort of like path. Even the distant comets and things follow this idea, and it enables you to say, they're not working in the same speed. The speed isn't constant, which again is something that I think's important. And then we hit the third law, the one that turns up in around 1620. And this is something I find absolutely phenomenal. To this day, I can't imagine how he sees this, given all he's got is all this data, and he's standing on a rock that's orbiting the sun once a year, and he's trying to work this out about all the other planets. This is, for me, amazing. It's this. The square of the orbital period of a planet is proportional to the cube of its average orbital distance, or t squared is proportional to r cubed. Now that is nuts. To see that, to notice that, when all you've got no Excel, there's no Excel here, there's no spreadsheet, there's no putting it into some kind of thing like SPSS, which is a weird thing, statistics program, you can just spit out correlations. This is amazing, because what it allowed him to do was to suddenly calculate everything in terms of comparing it to the Earth. We know that, given that we know that for the Earth, t is equal to 1 year and r is equal to 1 AU, what that actually meant is that if you worked out the time period of another planet in years, you could work out the distance it is away from the sun in units of Sun-Earth distances. Kepler doesn't know that the Earth is 1.5 times 10 to the 11 meters from the sun, but he does know that it's a sort of an average distance, and he can use that, therefore, to work out anything else. So if we do that with an example, so if we use that as a sort of example, we would say, I'm going to just find a planet. Let's take Mars orbital period in years. So Mars has an orbital of 1.88 years. How far is it from the sun? So if we're working in astronomical units, we would say that because we can deal with ratios, that what that means is that T1 squared of T2 squared would equal R1 cubed over R2 cubed. Because if you stick in a constant of proportionality to turn them both into equations, you would then divide through by it. He doesn't know what these constants are. So if we do this for the Earth, this is wonderful, because we can just say that, well, okay, that's 1 year, so that's just 1, and R of the Earth is just 1 astronomical unit, so that's wonderful, 1 AU, which is lovely, because 1 squared and 1 cubed is still 1, so we'd end up with 1.88 squared, over 1 squared, is equal to the radius, or the distance between Mars and the Sun, cubed, over 1 cubed. So just get rid of that. And we'd say that, oh, okay, that means that the cube root of 1.88 squared is the radius between the Sun and Mars in astronomical units. So cube root 1.88 squared, and we get 1.5 1.5 astronomical units. And that suddenly opens it out for all the planets. They can work out the distance to all the different planets based on the year and based on the distance between us and based on the year and distance between us and the sun. Now, we do know what an astronomical unit is. It's 1.5 times 10 to the 11 kilometres. But I quite like the idea that the difference is just one. I just like the idea that it's 1.5 times further away. So, if you want to pause the video and give yourself another go, I'm just going to look up a different one. So, if you want to, you can get, so if Jupiter is 5.2 AU away, what is its orbit period in years? And let's go with Saturn as an orbit. Saturn orbit in years is 29.5 years. So Saturn T is 29.5 years. So how many AU, how many astronomical units is it away? So go and have a go at that before we move on to the next bit. Okay, so let's deal finally, in this quite heavy theory one, let's deal with proving Kepler's laws. We're going to prove his third law. We're going to prove that t squared is proportional to r cubed. Now, that is the easiest way to do this, is to sort of disregard his first and second law and pretend that everything's going in a circle. Now, why? Is because a circle is just a form of an ellipse. So if it's true for a circle, it'll be true elsewhere. It is possible to do for an ellipse. It's just harder. It's just longer because you have to treat it slightly differently. But you end up at exactly the same result. So we're just going to deal. So at A level, we just deal with it for a circular object. So let's go with, there's the sun. There's our planet. And it's moving in a perfect circle. That's not a perfect circle. You know what I'm going to do? I'm just going to move the sun to the centre. There we go. That's a bit better. Now, what do we know? Well, it's moving in a circle. And we have a centripetal force which is acting towards the centre, and we know that that is coming from Newton's law of gravity. So, we know that the centripetal force is equal to Newton's gravitational law. Because they're acting in the same direction, they would both be sort of like, you don't have to worry about the minus signs. Centripetal force comes from mv squared over r. Newton's law of gravity is gm sun m over r squared. So what we can do is we'd say, okay, we would get, we cancel out our masses of the planets. So the mass of the planets doesn't matter. So we get v squared over r is equal to g m sun over r squared. That r we can get rid of because we've got an r and an r squared. So we end up with v squared equals gm over r, which is, remember there's that, that's a nice little result. V equals root of gm over r for anything in an orbit. That's a nice result to remember. So what is v? Well, v is the speed going around the circle. The circle has a circumference of 2 pi r. So your speed is 2 pi r over the time period. So what we end up with is that we end up with 2 pi r over the time period squared is equal to gm over r. That becomes 4 pi squared r squared over t squared is equal to gm over r. And then we just have to move things around. Move our r up to there, move our t squared up to there, and to clean it up a little bit, we'll move our this bit here, divide through by that to rearrange, and we end up with, that's got to be cubed, t squared is equal to 4 pi squared r cubed over gm, or time period squared is proportional to the radius of the orbit cubed. That is Kepler's third law for an object going in a circular orbit. And you know what? I think we'll stop here.